Good afternoon, ladies and gentlemen. My name is Mohammed Rana Basheer. My presentation today is on R factor, a new parameter that we developed to enhance the accuracy in estimating the position of a transmitter in a signal strength based location system. I'll first start with a brief introduction about what RTLS is and its application. Then I'll explain some of the objectives of my paper. Then I'll delve into some of the related works that were done in this area, and then I'll present my approach. And I will try to justify my theoretical derivation using some of the experimental results. And finally, I'll conclude with a list of what I have achieved. So, real-time location system is mainly used in places where you don't have a clear GPS signals. This could be a mine, a hospital, or it could be a factory floor where you want to track assets and personnel. In the currently available commercial systems, you can either find time-based approaches for locating a device, or angle-based, angle of arrival-based approaches, or you can see the signal strength-based approaches. And however, the cost, the accuracy, and the time it takes for calibration has taken a lot of flack, and it actually has resulted in the limited adoption in the industry. In this paper, I'm only looking into the signal strength approach. In an ideal world, the signal strength should vary inversely as the distance as shown here. But as you know, things are not as ideal when you put this in practice. So what we did was we did an experiment in which we collected the signal strength distribution over our lab. This lab, the layout that you see over here, measures approximately 12 meter by 13 meter, a typical lab environment with a lot of chairs, machineries, and equipment and all those things. And what we used was a wireless transmitter that is operating at 2.45 gigahertz. The frequency was selected because it falls in our ISF band, free ISF band. And what we did was, the position of those transmitters were at those circles marked 1, 2, and 3. And all these grid points that you see, that's where we collected the radio signal samples. And if you see the signal variation over here, it's not smooth as you have seen in an ideal plot. You see a lot of values and all, but from this transmitter location, as you move away from it, you see the signal strength decreasing. The region that you see over here where it's completely zero is because it falls outside our lab. This is the area, that's why there's no data there. But you can see that the average signal is reducing. However, when you go to the second transmitter over here, right, that you collected, the interesting pattern is that initially it starts decreasing and then it starts increasing towards the corner, one corner. And for the third transmitter, it's even more kind of totally weird in the sense that it starts increasing as you go towards the corner and towards the end of the wall. Now, what is the reason for all this variation? The variation, what we have, from the literature, we can find that these are because of multipath fading. What you can say is fast fading, where you have at a single receiving point, you have signals coming from multiple directions because of reflection, scattering, and all. And when they interfere, they can either constructively or destructively interfere. And second, then you have the slow fading. That's when you have walls, partitions that are preventing the main signal, the main line of sight component of the signal. And then third, you have asymmetry in your antenna propagation patterns. It's not, even though you take a quarter wave dipole antenna and assume that it's going to be uniform around azimuth, it's not. It's not. When you take an actual antenna pattern, you can see that difference. And the final thing is you have co-located networks and you have atmospheric effects and all those things connected in the picture. Now, with all these problems there, what is the advantage of using an RSSI, that is a signal strength-based method for locating a device? The bottom line is it's very cheap. You can basically have an RSSI data available on pretty much every wireless device. Your iPhone, your Wi-Fi, Zigbee radio, all those devices have an RSSI data that is available. So basically providing a localization service in such a network is just a software upgrade. Now, what is the flip side of it? The main problem is the RSSI is not very accurate. It has been proven in certain papers that there is some fundamental limits in getting really good accuracy with RSSI. And time-based and angle-based approaches have shown to have really high accuracy, especially when you have a clear line of sight. And the main limiting factor is that you need to periodically reprofile the factory floor. And that is to keep all the parameters that are involved in your estimation consistent. Now, what is the objective of my paper? What I am trying to achieve primarily is how can we quantify the errors that are occurring in localization estimation. The second thing is I wanted to find a single parameter that I can use easily and in real time to classify the devices or the receivers that are estimating the position of the transmitter and then grade them. And finally, I wanted to see, is there any method that I can use to improve the accuracy, to basically get around the fundamental limitations that are available in some of the existing RSSI methods. So I explored into something called spatial diversity and channel diversity in general. So the first paper that I looked into, which actually looked into the classifying of the devices, used a Gaussian-based method. Basically, what it meant was the signal that is received on a good signal that is received by a receiver has a Gaussian distribution. But that is only valid when you have a really large signal-to-noise ratio. So if you use a Gaussian check to find out if a receiver is having a good quality signal for localization, the main problem is you probably end up with excluding a lot of receivers that could otherwise have provided you better accuracy in estimating the position. The second paper, basically what they did was try to use some of the statistical tests like chi-square tests to classify the signal into different classes like rally, when you don't have a line of sight, or like a Ricean, when the line of sight is between a really high value and a zero, or it is completely like a Gaussian when you have a very good signal. Now the problem with the chi-square test, that anybody has done it, is that you need a large number of samples in order to really get a good data, good results out of it. And of course, when you are dealing with trying to estimate positions in real time, this is definitely not a real time solution. Now, the contributions of my paper is basically that we developed a new parameter called R factor, which is nothing but an estimate of the mean square error in location estimation. And second contribution is that we have shown theoretically and experimentally that by using channel diversity methods such as combining different antennas using selection combination, we can actually get a better localization experiment. Now, people who have been using communication equipments, they know that channel diversity improves signal-to-noise ratio, but signal-to-noise ratio improvement, does that translate to improving the localization accuracy? That's the main thing.